Hey, what's up? It's Jake from Nimbus DevOps, and I'm here to talk to you today about generators. Not the cool ones that you use to power your quad or your RV, but a very powerful programming tool. So they're based on the concept of iteration, and as we kind of mentioned before, as I clear this out for you, they allow for a coding pattern that combines elegance with some efficiency benefits. So there's really two different types, generator functions and generator expressions. So the function is similar to a regular function, but instead of returning a result through a return statement, they use yield, which allows them to suspend and resume their state between each call. Whereas the generator expression is more similar to like a comprehension, but instead of returning a list, it returns an object that produces results one by one, as you would imagine, like something that's being generated one thing at a time. So that's kind of the overview, and I'm just going to go over generator functions for now. So functions behave like regular functions, except for one difference. So instead of collecting the results and return them all at once, as I was saying, they are automatically turned into iterators that yield results one at a time when you call next on them. So they're automatically turned in their own iterators by Python. It's kind of theoretical, so I'll give you a little example. So let's say that you had to count out loud from 1 to a million. As kids, we used to do this, like, I don't know, um, some people do this all the time. Uh, at some point, you're asked to stop, right? Your parents or your teacher is like, okay, you need to stop now. Um, but after some time, like you go to recess, you might want to keep going. At this point, the minimum information you need to be able to go would be, what do you think? Well, probably just the last number. Like, where was I? I don't want to start over. So if you stopped at some crazy number in like the 30,000s, you'd need to know that to keep going on. But it's kind of hard to remember. But the point with this is you don't need to remember all the numbers you said before, or you don't need to like have them be written down. Um, But if you can do that in your brain, then you're actually functioning like a generator function. So let's take a look at a generator function. So I'm going to define a function called getSquares. And I'm going to pass an argument n. And I'm just going to say I need you to return a list of x squared for x in range, whatever n is. Okay, pretty simple. And then after that, we'll just print SQL update. We're gonna print get squares, and we need to pass a value. So let's pass 10. And if I just type Python and then gen, I can see all of the squares. And we did something very well similar but identical in a previous uh, lesson, I guess you want to call it, video. So this is kind of like what I would call like a classic function approach. Okay, so let's try it using the generator method. So we're going to do a get squares gen, which takes an argument n. Okay, I really should like put this on my function name, probably. I think makes more sense. So I can put the generator function approach. Okay, cool. So in here, what I'm going to do is I'm going to say for x in range n, whatever that is, we just want to yield x cubed, or x squared, sorry. Okay, so in this case, remember, we yield, we don't return. Don't return. Okay, and then here, what I'll do is I'll just print out the get squares gen and pass the number 10. Okay, so let's take a look at this, and we should get two lists, generator object get squares gen at blah. The result of these two print statements is the same, but there's a huge difference because get squares is a classic function that collects all the squares of numbers in 0 through n in a list and returns it, whereas get squares gen is a generator that behaves very differently. Each time the interpreter reaches the yield line here, it's going to be executed differently, right? It's going to be each execution is suspended. The only reason print statements return the same result is because you get fed get squares gen to the list constructor. Okay, so in this case, like if I was going to do this, what I would have to do is before I get to this, and we saw this with how we were doing things earlier to avoid these strange unusable objects, is you can wrap them in a list function, and then that construct is much more meaningful. Whereas this, you probably have zero clue what this means, and you would be right, and neither do I. So let's take a look at this. So define get squares gen for x in range and yield x squared. So if we look at this way, let me comment this out. So let's say that I have a variable squares, and I make this equal to get squares gen with a number 4. Okay, so this creates a generator object. Okay, and then when we print squares, what's happening here is the generator object get squares gen at this. This is what we're really getting, right? So then what's going to happen is it's going to go print next squares. And if I just were to copy this, just this line though, 3, 4, and then here we'll say the following raises stop iteration, and you can probably see why already. The generator is exhausted. All right, it's not tired. It ran out of numbers, right? So it can't next through anything. So in that case, any further call to next will keep raising stop iteration. And then we can see an example of that by calling it one more time. So let's see what happens here. Boom. So I have the print squares, which we saw originally up here, prints this strange object, right? And then I'm going to print squares first, and it's going to do the next one, which is the first one. And then the next one at position 1, and the next one at position 2, and the next one at position 3, although it's not a list yet. So, and then if I print it again, it's going to go, uh-oh, stop iteration. I ran out of numbers. You need a bigger number. Now, if I were to change this to 5 and run it, you don't get an error because there's another number for it to find. But if I change it back to 4, as you can see, you get a stop iteration error. So each time you call in the generator object, you either start it like I did with the first call, or the first next, or you make it resume from the last suspension point, which is any other next. The first time you call next on it, you'll get 0, and then all the way through 9, as you can see there. So this explains how a for loop works, if you think about it. So when you call like for k in range n, here I'll just type it out so you're not thinking about it, for k in range n. So if you were to make this for loop and then like do something, right? Then what you actually have here is you have a generator that's going to loop through some sequence or object a certain number of times until it reaches a stop iteration. Okay. So what happens under the hood with the for loop is the for loop gets iterator out of range n and starts calling on it until stop iteration is raised, which tells the for loop the iteration has reached its end. So having this built into every iteration aspect of Python makes generators pretty powerful because once you've written them, you can plug them into whatever you want to. So you're probably asking yourself, why would you use this instead of just a regular function? And that would be a good question. Um, really, the answer is to save time and most importantly, memory. So I did a little bit about performance in an earlier video with a very janky time kind of thing with time it, but we'll get into that later in more detail. But for now, let's just focus on the fact that it allows you to do something you can't do with a simple list. So let's say, for example, you want to analyze all permutations of a sequence. We've done this before, but we're going to do it now with a generator. So if the sequence has a length n, then the number of its permutations is n, or n factorial, right? So this means that if the sequence is 10 elements long, the permutation is like 3 million something. But the sequence of 20 would have like some gigantor number that I can't even think of, and they grow fractally. So imagine you have a classic function that attempts to calculate all these permutations and put them in a list and then return it to you. With 10 elements, it would probably take a few seconds. But if you had 20, it would take like thousands of years to. Factorials are insane. It would take thousands of years and billions of gigs of RAM to do it. On the other hand, if you use a generator, you can start the computation, give you back the first permutation, then the second, and so on. And you won't have time to process all of them because there's too many, but at least you'll be able to work with some of them. Because the problem with running a program like that is it's going to build all these things in memory and then return it to you. Well, the problem with iterating like that is that you're not getting any data back, so you literally have to wait. And if you do something like that, it's just going to take up all of your computer resources and it's going to crash or it's going to freeze or do something. But with a generator, you can work with these pieces of data one little bit at a time. Um, so generators are pretty valuable in that case because it makes possible something that like those types of list iterators wouldn't be able to do. So to save memory and time, we should use a generator function as much as possible. It's also worth noting that you can use return statement in a generator. It will cause a stop iteration to be raised, effectively ending that iteration, which is important because a return statement were actually to make the function return something, it would actually break the iteration protocol. So Python's consistency prevents you from doing this. Let me give you a little example here. So if I were to let's make a gen2, oops, Python scripts, gen2.py. I'm gonna need another folder soon. So here's an example. So if I define some sort of geometric progression and I pass to a coordinate and say k equals 0, and then while true, so basically a while loop, right? Result equals a times q to the k power, and then we're going to say if result is less than or equal to 100,000, then we want to yield the result. Else, return. So you see that I'm returning. And then we will just increment k by 1. And then here, say for n in geometric progression, to 5, print n. So in this case, this yields like all the terms of a geometric progression, like aq squared, aq cubed, aq to the 4th power, etc. When the progression produces a term that's greater than 100,000, the generator stops with this return statement. Running the code, if we run it now, you'll see this. Okay, so 2, right? And then we have while true 2, and then we start at whatever number, k being 0. So 2 times 2 to the 0 power is 1. 2 times 1 is 2. Okay, It was less than 100,000, so it yielded a result. It did not return. It increments k by 1. K then becomes 1, and then it says A, which is 2, right? And then Q, well, in this case, this is 5. Um, Q5 to the first power would be 5. So 2 times 5 is 10, which is less than 100,000. So we're going to yield a result. And then increment k by another one. So if we were to look at this again with k equal to 2, A is 2 times Q is 5 to the now second power. 5 times itself, or 5 squared, is 25. 2 times 25 is 50. Result is less than 100,000. Yield the result. Here's 50. And this will continue going until we get to k being a value of 0, 1, 2, 3, 4, 5, 6, 7, 8. And it could do it. When k was equal to 9, it said 5 to the 9th power times 2 was greater than 100,000. So it did not yield a result, so it just returned. It breaks this it breaks the iteration, comes out of it, and then completes. And that's where we get our results. So that's what this does. That's the explanation of it. The next term is like 156,250. I think if you go Python, we can do a simple math here. Do 5. Well, you can even write it like so. A, right? A is 2, and then Q is 5. So if K is 9, and we have A times Q to the K power, that's a big one. That's way too big. So if I did K equals 8, and I run this again, you can see 78,000, yada, yada, yada. So this is essentially a generator. As you can see, it yields a result with some return. If this number was huge, then I could do that. Now we knew that we left off here, so we could process this data in whatever you're using it for, and then once we're finished, we could come back here and say, hey, I only need if result is greater than 100,000, but maybe less than 1 million. Okay, you could do something like that. So anyways, that is going to be it for now. As soon as you think you got your head wrapped around that, feel free to watch this again if you need to. I'm going to kind of break this down a little bit more, and we'll get a little bit deeper into this whole concept of using the next function.